Welcome back to Calculus 2. In this video, we're going to talk about power series. One of the big topics when you're talking about sequences and series, mainly because of some of the applications of them. They're very powerful. We're just going to introduce them in this video, maybe do some examples with convergence and divergence. We'll go into some of their more esoteric properties in the next video, and then talk about some special cases in the one after that. So first, what is a power series? Well, a power series about x equals 0 is a series of this form, c sub n x to the n. You could think of it as a geometric series, but your constants change with each term, whereas a geometric series, this is just a constant. So a geometric series is actually a special case of the power series of this form. A general power series about x equal a is the same kind of looking thing. It's just instead of having x there, it's x minus a. So this formula actually does hold for this one, because if a is 0, you just get x to the n. It just has a formula for constants, and then a x minus a raised to the n. Now this is a variable. We'll actually see, depending upon what you input for x, you may or may not achieve convergence of your series. Each coefficient is a constant, but there may be some calculation involved in getting that constant. So this is the only theorem we're going to prove in the video today. But it says if the power series converges at a number, then it converges absolutely for all x with x less than c in absolute value. So all x that's closer than that value to 0. So if you have some c where it converges, every x that's closer to 0 than that c, it will also converge there. And if the series diverges at some number, then every x farther away than d from 0 will also make the power series diverge. So let's do the proof for this. So we know the series converges for x equals c, so let's look at that. Suppose n equal 0 to infinity a sub n c to the n converges. Then the limit as n goes to infinity of a sub n c to the n has to go to 0. We know that true by the theorem we proved right before the nth term test. It was actually the result that gave us the nth term test. So there is an integer, capital N, such that a sub n c to the n is less than 1 for all little n greater than big N. Now, this would be true for any number. I just picked 1, but it would certainly, there, because it converges to 0, it will get smaller than any number but 0. So you could make it be 2, you could make it be 3. We're just picking 1 because we want to get a specific result. And just doing an algebraic manipulation of that, a sub n in absolute value is less than 1 over the absolute value of c to the n. Now take any x such that absolute value of x is less than c in absolute value. Now remember, what we're trying to show is that it has to converge at any x that does this. Any x that has a smaller absolute value than c, that's closer to 0 than c. So we know absolute value of x over absolute value of c is less than 1. Taking this down and multiplying both sides by x to the n gets us absolute value of a sub n x to the n. Doing that is less than absolute value of x to the n over absolute value of c to the n. Make that a little bit more clear here. Times for little n bigger than capital N. Now we know this is of course just equal to x over c in absolute value to the n. We can actually use a comparison test now, because this is the absolute value of our series. You know, if we were looking at the series sum a sub n x to the n, which we're supposed to show this is convergent, since that is convergent. Well, if you look at this series, the sum of x over c to the n, that is a geometric series. So the sum x over c to the n is a convergent geometric series. Since the inside, the absolute value of x over c is less than 1. We said that just right there. And remember, geometric series converge when their common ratio is less than 1. So, a sub n, absolute value of x to the n. I'm just going to put an absolute value. A sub n x to the n in absolute value is convergent by comparison test. And I'll go ahead and say, so a sub n x to the n is absolutely convergent I'm just stating the conclusion here. For absolute value of x less than absolute value of c. I think that proves everything we were asked to prove. Let me go check it to be sure. So if we converge at some c, then it converges absolutely for all x with absolute value of x less than absolute value of c. If it diverges at d, then it diverges for all x with x greater than d. I don't think I've done the diverges yet. Alright, let's go to the next page then. So this time we have a number d at which it diverges. Suppose sum n equals 0 to infinity of a sub n d to the n diverges, and we take x with absolute value of x greater than absolute value of d. And I think we're just going to do a proof by contradiction. If the series n equals 0 to infinity of a sub n x to the n converges, then sum n equals 0 to infinity of a sub n d to the n must converge by the work we just did. Because we showed if it converged here, it would have to converge at any number closer to 0 than it, which d is. So this would have to converge, but we assumed it didn't. This contradicts our assumption. That the sum a sub n d to the n diverges. So the sum n equals 0 to infinity a sub n x to the n must diverge. Alright, and that's the whole proof. Converges at a number. Every number smaller than it in absolute value must also converge there. If it diverges at a point, then for all x that are greater than that point in absolute value, it must diverge there as well. This is proven in the book as a corollary. It's a fairly lengthy proof, but it's pretty simple. So I'm going to leave that to you guys. If you want me to go over it at some point, I'll be glad to. But it's on page 620 in our textbook. But what it says is pretty much the natural consequence of what we were just talking about. So if you have a series that converges somewhere, it might just converge at A. All power series basically converge at A, because if you plug in A for x, it's just going to be 0. It's a constant thing. It converges to 0. But that's really a trivial case. There is a positive number r called the radius of convergence, such that the series diverges for x with x minus a greater than that, but converges absolutely for any x within that radius. So if your distance between x and a is within the radius, you will converge absolutely. Greater than the radius, you will diverge. It may or may not converge at the endpoints when it equals the radius. So that's a possibility. Some finite number r. The series might converge absolutely for every x, so its domain, it's basically its radius of convergence, might be infinity. Or it only converges at x equal a, diverges everywhere else, in which case the radius of convergence is 0. So one more bit of theory. This is the last new bit of theory. The last slide we're going to look at is just kind of a summary of everything we're going to do in the exercises. We're going to be looking for these radii of convergence. Generally, when we look at one of these things, we're going to be trying to figure out where they converge absolutely, so it's natural to use the ratio or root test for that. Ordinarily, this may be an open interval. Occasionally, it might converge absolutely at one of the endpoints. But if we have a finite radius of convergence, we'll test for convergence or divergence at the endpoints. If it's infinite, I mean, the endpoints are infinity. There's no point in trying to test those for convergence or not. And this last thing is just assuring us that once we find the radius, we don't have to go beyond it when we're checking for conditional convergence. Everything that's greater than r in distance from the center of A is going to diverge when we plug it into the power series. The only things we have to check are where it equals r at the endpoints. Don't have to check any closer to that. So all of these things will be symmetric about a center point. It's just trying to figure out where that is. Alright, let's do some exercises. Our first problem is problem 6 on page 624. Radius and interval of convergence, and specifically we're going to compare where it might converge absolutely or conditionally. First off, since I got x there, do ratio test. That would be 2x to the n plus 1. Then I divide by 2x, like so, to the n. Doing the ratio test, infinity. So that's just going to give us 2x. Limit as n goes to infinity of 2x. Well, no, it should be an absolute value as well. Note there's no n in this, so this is just 2x in absolute value. Now, ratio test, for it to converge, absolutely, this needs to be less than 1. So that means absolute value of x has to be less than 1/2. This is the radius because you notice there's no x minus a, so our center of our interval is just at 0. But you can honestly just tell the bound on x just from looking at this. Taking away the absolute value, this means x is between 1/2 and -1/2. So this is the interval of convergence, I think. We got to check the endpoints. If I plug in 1/2, x equals 1/2, we will get 1 to the n, sum n equals 0 to infinity. 1 to the n goes to 1, so it diverges by nth term test. And then if I look at x equal -1/2, you would get 2 times -1/2 would be -1 to the n, which diverges. So also series diverges by nth term test. So the radius equals 1/2, and the interval of convergence is -1/2 to 1/2, not including the endpoints. And B and C are both the same in this case, so absolute convergence certainly is going to imply conditional convergence, but you might have conditional convergence at the endpoints as well. In this case, we did not. Let's go to the next problem. On this problem, same instruction. We do our work again. For absolutely convergent, remember we're doing absolute values, so I can ignore this. So if we do the ratio test, it'll be x plus 2 to the n plus 1 over n plus 1, and then divided by, so times n over x plus 2 to the n. So that's going to get us n over n plus 1 times x plus 2. In absolute value, the limit as n goes to infinity. And remember, of course, no n's in this part. This part just goes to 1, so this is just going to the absolute value of x plus 2. We want this to be less than 1 in absolute value. So this actually tells you straight up the radius of convergence is going to be 1. And if you want to find the interval of convergence, well, x plus 2 is less than 1 is greater than -1. So subtract the 2, -3 less than x less than -1. So it's -3 to -1. Now we do need to check what's going to happen at the different endpoints. So if I plug in x equal -3, we will get the sum n equal 1 to infinity, -1 to the n. If I plug in -3 up there, I'll get -1 to the n over n. So that's going to be the sum n equal 1 to infinity of just 1 over n. That is a divergent p-series. If we look at -1, that's going to be -1 to the n times +1 to the n over n, which can really ignore the 1 to the n, so that's n equal 1 to infinity of -1 to the n over n. This definitely does not converge absolutely, but it does converge conditionally. Because if you do the alternating series test, converges conditionally by alternating series test. Alternating series assumes that's there and ignores it and pays attention to the rest because that's what's going to determine whether it converges or not. If it converges to 0, is always decreasing, or at least after a certain point, and is all positive, which is certainly true of all the 1 over n's, then if it's an alternating series, it will converge by AST. Values of x where it converges absolutely are -3 to -1. Converge absolutely. Converge conditionally are from -3 to -1 with a square bracket on -1. So there we go. Radius is 1 because the center is at -2. You can tell x minus -2, so the A is -2. It converges absolutely just within that radius. It converges conditionally, actually on the edge of that radius on the right, not on the left, but that's the way it goes. Alright, this one. Find the series radius and interval of convergence. Well, we do our ratio test, 3 to the n plus 1, x to the n plus 1. This is another one centered at 0 over n plus 1 factorial times n factorial over 3 to the n, x to the n. This will get us 3 on the top, x on the top. This will cancel out with the n factorial when you take off the n1, n plus 1. So that's 3x over n plus 1. Limit as n goes to infinity. Note we do have an n this time, and this is going to 0, which is always less than 1. This means it doesn't matter what the x is, it always converges. So converges absolutely on -infinity to infinity, r equals infinity. So that was pretty quick. Pretty nice. I think this is our last one for this video. If we look here, find the series radius and interval of convergence. Well, it is going to converge absolutely and conditionally. Let's see, where is that going to happen? Well, first off, let's rework this a little bit. I guess I can set up the... yeah. I'll see what the ratio test looks like first. That'll be square root of n plus 2 minus square root of n plus 1 times x minus 3 to the n plus 1 over square root n plus 1 minus square root n x minus 3. I think I really ought to do a little work with this first, because, well, you know, I think it'll be easier if I do some simplification work on this first. If I rationalize the numerator, square root n plus 1 minus, or plus square root n, square root n plus 1 plus square root n. That'll get me n plus 1 minus n over square root n plus 1 plus square root n, which will just be 1 over, so it'll basically be x minus 3 to the n over square root n plus 1 plus square root n. Sum n equal 1 to infinity. No, that won't be any nicer. So, working on this thing, I mean, it seems like you're going to have to do the same rationalization we did before. We already did this before. We know when we multiply top and bottom by this will become x minus 3 to the n over square root n plus 1. Oh, I see. No. I see. I see. Yeah, let's work with this. Sum n equal 1 to infinity of x minus 3 over square root n plus 1 plus square root n. It is better to have the plus in the middle. That it removes the indeterminate aspect of it. So you plug in n plus 2, you do ratio test. That'll be square x minus 3 to the n plus 1 over square root n plus 2 plus square root n plus 1 times the flip of the original, so square root n plus 1 plus square root n, forgot my plus 1 there, over x minus 3 to the n. So of course you're just going to get x minus 3. As far as these go, if you put them over each other, square root n plus 1 plus square root n over square root n plus 2 plus square root n plus 1, limit as n goes to infinity. I'm not actually sure what's going to happen there. It seems like it'll just go to 1. Because you divide top and bottom by square root of n, you would get square root of 1 plus 1 over n plus 1 over square root of 1 plus 2 over n plus square root of 1 plus 1 over n if you divide top and bottom by square root n. And that's going to 1 plus 1, 1 plus 1. Yeah, it's just going to 1. So all of this, it's just going to x minus 3 in absolute value. That has to be less than 1. So this is the radius of convergence. Sorry this sprawled all over the place. Just the nature of thinking about it. Sometimes your scratch gets a little messy. So it's greater than -1, less than +1. So our interval is going to be from 2 to 4. And if we check the endpoints, let's see, down here we got it. If I plug in 4, that would be the sum n equal 1 to infinity of 1, if I plug in 4, over square root n plus 1 plus square root n. That'll be equivalent to, I could do a limit comparison with 1 over square root n. And if I did that, yeah, they would have the same convergence or divergence. And 1 over square root n is a divergent p-series, so divergent. If I look at sum n equal 1 to infinity of, what's the other one, 2, x equal 2. That'll be 2 minus 3, so that'll be -1 to the n over square root n plus 1 plus square root n. Now that will converge conditionally by the AST, the alternating series test. So converge absolutely on 2 to 4, converge conditionally on 2 to 4 with a bracket on the 2. That'll be it for this video. Next time, we'll look at some more theorems involving power series, and then move on to a few exercises before we finish. After that, we'll talk about Taylor series and Maclaurin series, which are special cases of power series. They have some pretty rigid conditions on what the coefficients have to be. See you then.